Are waiting to come in. Cindy, a few more?
I actually let everyone, and I'm going through them individually right now.
Okay.
So
We
you
have
can
plenty.
start.
Okay, yeah, we have plenty of time today, so hopefully, unless I get really chatty. So I've left the Rogue gallery up for people, but I think now I'm going to go ahead and share screen and start a couple of presentations. So one moment. Okay, so you should be able to see my online presentation. Can everybody see that? Yes or no? Okay, great. And you guys can all hear me
Yes.
fine. So, okay, well, welcome everybody. I'm so excited to do our third annual HPC User Training class. It's usually a lot of fun, and it's just a broad but not very deep dive into HPC, the world of high performance computing. And then by the end of it, we hope you're all pretty familiar with how things are done on our systems and on HPC systems in general. We have a group of mentors. I'll introduce them. And if they're here, hopefully they were able to attend. Well, they're very helpful, so you guys can contact them with questions. And today we'll do an introduction to the program. I'll introduce the mentors. We'll do a little bit of orientation about the program and how it works and the timelines and things like that. And then do an overview of high performance computing, and then we'll conclude hopefully with enough time for you to all begin the process of registering for an account on Expanse, which means getting one on Exceed. And oh, this little word cluster represents the different majors and fields of science that participate in our HPC training. So welcome, and the mentors are myself, I'm Mary Thomas. I'm the HPC training lead and computational data scientist at SDSC. And Marty, are you here? Marty Candace, Martin. I'm not sure everybody was able to make it. If you're here, you're muted. But Jeff, are you here? Marty is with the user support group, and he develops a lot of our code and our exam. He's a Singularity container expert, an HPC expert, and he'll be doing a few of our presentations this course. And Jeff is a visualization technology and education technology specialist. Bob Sinkovitz is the director of training and co-PI on the Exceed project, and he leads a user group in computational science. Are you here, Bob? And I'll just go ahead and introduce people then. Mahi, I think I saw that you are here. Would you like to introduce yourself?
Yeah, sure. I'm Haidar Tatineni. I lead the user services group here and also co-PI on the Expanse project and also on the Comet project. And I'm going to help out with some of the tutorials during this course.
Yeah, we love Mahi. He gets us sometimes queuing privileges, so we want to be nice to Mahi. Cindy, and nice to Cindy. She keeps us all organized. You introduced yourself, but why don't you do it again?
Hi, everyone. I'm Cindy Wong. I'm the event specialist with the center, and you have been getting lots of emails from me, which I apologize, but hopefully you enjoy this series.
Yeah, and I'm not sure Susan, she's also part of the group putting together the events and organizing people. There'll be more people added, like Nicole Walter. She'll be doing all the account creation for you. So listen to Nicole when she sends you an email, and when you set up your account, we'll go through that process. She's the one who will get you onto Expanse. So just a little bit of evolution in parallel computers has occurred in the last few years. This is a real project that was around in 2003, and they kind of won an award on the low 500 for the cheapest cost per flop. I love to show this one because that's what computers used to look like. And someday when we're all able to get onto campus, we'll give you a tour of the Supercomputing Center, the machine room, and you'll see how it's evolved. But what they did, these are people from Oak Ridge, they went out and scrounged up every unused workstation, that desktop that they could find, and put them together with open source parallel software, and had the cheapest cost for flops, and they had a whopping 20 megaflops. But it's based on the story of Stone Soup. If you haven't heard the story, it's a fairy tale or an old story about a town that was very, very poor and hungry and starving. And one of the town members put a pot to boil with water and a rock in it. And they said, "What are you making?" He goes, "Well, I'm making soup." And they said, "Well, there's not much in that." And he goes, "No." And one town person said, "Well, I have a potato." So he went and found his potato. And another town person said, "Well, I have some celery." So he went and found some celery. And bit by bit, the people in the town put together pieces of different food, and they ended up building a big pot of soup. And that was the theory behind this. So that is what they used to look like. They're a lot bigger now. This is a summary of our newest machine at SDSC, the Expanse computer. The theme is computing without boundaries. It has about 5 petaflops, and it has several different components to its architecture, and it continues with the theme of computing for the long tail of science as well. There are applications out there that need to run on 200 million cores, and their applications can score, and that's great. But there's a lot more of us that need a few thousand cores or some different type of computing architecture, and there's a lot more of those jobs. So if you integrate the jobs out in the long tail of science for number of cores needed, you'll find there's a tremendous amount of people. On our last version, Expanse is an upgrade from the Comet computer. There were 40,000 users. So there's quite a few people we anticipate using Expanse. This is a 5-year funded project with NSF with an additional 5-year extension worked into the program. And so this will be around for 10 years, and there's plans to upgrade it. So we have these scalable compute units where each rack is a standalone system with the CPU and GPU and some storage right on the rack. And then we also have high speed performance, 128 petabytes of storage there. We have distributed cyber infrastructure integrated in cloud computing, open science grid, and a lot of other innovation systems coming out, like the composable systems. And we'll have a webinar on that in the spring. Well, we're almost in the spring, but high throughput computing, science gateways, interactive computing, containerized computing, cloud bursting. So it's an exciting system, and we'll welcome all of you on it. You'll all get accounts on Expanse and its various components that are available. So HPC User Training, which is where this course is, it started out as a program for students to involve them in the center and get them interested in a program called the Student Cluster Competition. But it's expanded to more people interested in this in our local community. So this year will be the first year we're recording. And Joey, you could start recording anytime you want. So we'll be recording this year. It'll be the first year. So usually we're in person. There's an instructor, some mentors, and the students, and then we help you with questions at the end of the presentation. So the format this year will be the recorded presentation, and then at the end we'll break off the recording, and mentors will be around, and the club students from the club will be also available to mentor. Most of them survived and participated in our student cluster competition team in the fall at Supercomputing. They did very well. They were 4th ranked overall score. And so they are very good experts now in HPC. So this is free. And at the end of it, there are some outcomes that might motivate you, like a certificate of completion, and for the students, co-curricular record credit, and the opportunity to participate in some of our more advanced club projects, which I'll introduce briefly. The scope is to study HPC architecture, CPU, GPU. Unfortunately, we don't do quantum computing yet, but in a few years, I'm sure we will. To learn the basics of parallel computing, MPI, C, Fortran, possibly other languages, running some applications and looking at performance and different numerical methods, a bit of cloud computing, some visualization and analysis of big data sets, and an introduction to machine learning that's so popular now that we like to include that in our training. For 2021, this is sort of the basic overview. We broke it up this year into a series of sessions in the winter and spring quarter. The last two systems we did 10 weeks straight all the way through, and it competed with key phases of the quarter, like final exams, which sometimes go on forever. But so we broke it off so we would have a first session with 8 sessions in the winter quarter. Then we take the break with the spring quarter, and we also started it a little bit later to help people hear about the program. And it's not too late to register. We have registration open till the end of January. And then session number 2, it begins in April. The workload is a regular attendance is very helpful, of course, but we are recording it. And to successfully complete assignments and maybe 1 to 4 hours a week in addition to coming to the weekly session. The assignments are pretty basic, and they're meant to show that you are able to demonstrate running the most basic examples. It's more at the hello world level of high performance computing, but there's still a whole lot of concepts to build up. And so we do like to see you complete these assignments. The metrics include completion of tasks and some credit for experience. And this is really more for the students who are trying to get co-curricular record credit. I'll talk about that down here. So you'll get a certificate of completion, and you'll be able to have an account with allocations under our training grant on Expanse for 1 year. The caveat is you can't abuse it and use up all our allocations. In that case, we will work with you and mentor you to help you get a startup allocation that can run from 1 to 3 years. That's also part of what we do. If you've completed the training, you'll get a lot of support and opportunities if you're a student for internships. So UCSD students can get co-curricular record. If you don't know what that is, that's we created these CCR activities that will appear in the student's transcript with a full description of what they did, what they learned, and some classified student learning outcomes that are part of a broader nationwide education definition, defined by education initiatives. So here's our schedule update. Keep an eye on this schedule. There's the link to it. It's right where you went to register. It can change. This is tentative based on availability of speakers, and maybe we learn during the sessions that something else needs to be taught, but it's pretty predictable. So the student program, HPC student, the user training comes out of HPC students, which has several activities. We interact with the club quite a bit. Our goal is to bring students from campus into what we do at SDSC. We help sponsor internships, the HPC training, and general training on other topics than what we do in this session. Building and supporting more internships, excuse me. And one of the main projects, in addition to the student cluster competition, is the Raspberry Pi cluster build out, which will start in spring. And we're still working out the logic and the logistics for doing this remotely. But we will be doing something where the students who are members of the club will be building their own cluster and managing it and working on it. And we hope to maintain that cluster over the long term. And then also we do a lot of activities at Supercomputing, the annual meeting, student cluster competition teams. We were selected. We're already planning next year. 4 students from last year's team are available. We'll be looking for more members on that. And then we send student volunteers. We had 4 selected in 2019. This year, none because it was virtual, but there's still value in having this for your student vita. And all expenses, if we travel, are paid by SDSC and club sponsors. So Jacob is here and he will talk about the club next. I'll mention Supercomputing 21 and the student cluster competition. Jacob will also talk about that. It's very exciting. We're very proud of how our team did. I've had several teams, and this SCC started in 2007 to bring high school and college students into the world of high performance computing. And hopefully, we get more people trained and excited about this amazing industry. How to compete, it's competitive, so we work hard, and this class is the beginning of training our students for next fall and what every other kinds of competitions that we can participate in. We learn about it, and the steps to get there are we learn about HPC, we submit, and if we're selected, we start learning the programs, and we spend the spring and summer practicing and getting ready for a very busy fall. It's fun. Team Superscaler, they did really well. There is the team. Jacob is president of the Supercomputing Club, and they did wonderful. And they had several HPC applications to learn, and you can read more about those online. The new thing that they did this year was put all the teams in the status of where they were on every one of the applications online. It has since gone down, which is sad. But what we're pleased about is for a first year team, we were placed 4th in total score points overall, and we were the 3rd fastest for high performance conjugate gradient, the 6th for the IO 500 bandwidth. The team that won from Tsinghua University, they designed their own network. So they put some good work into it, but we had a lot of fun learning how to run all these codes. It was all done on the cloud, and we had to learn how to manage the cloud computing budget. Normally you manage the power, so that was fun. And the activity coming up will be the Raspberry Pi cluster. So we have a lot of sponsors. They're amazing. I don't know if they're here today, but starting with AMD and NVIDIA and Microsoft Azure, where we ran the competition. Amazon Cloud Bank helped us manage our accounts, NERSC, ARM, Oak Ridge. We have a lot of sponsors. NSF, UCSD, SDSC, and the Exceed project for letting us use resources on Exceed. Okay, so I can briefly stop and see if there's any questions, or there's people that can also answer them. Yeah, so I'll get that. Thank you, Dario. I see you guys are on top. Yeah, we're recording, hopefully. I'll get into some of the details. This talk is uploaded. I need to update it, of course, but any other questions about just the overall program? I went through that pretty quickly. And if not, you can send me an email. So I'm not going to go back into display mode. What we're going to do is, this is week 1. Jacob, are you here? Xiaoyi, are you here?
Yes, I'm here.
Okay, great. I'll let Jacob speak and then we'll get into the tasks for week 1. But if you haven't already registered, did Cindy post the link to the registration? It looks like she did. And then we'll talk about how to get your Expanse account when Jacob is done. So I'm going to stop sharing. And you guys already know where the GitHub is. And all of our talks will go up there and all the work assignments that you need to do. You can have the comm, Jacob.
Okay, just give me a second. Let's see.
While we're waiting for Jacob, any questions?
All right.
Okay.
How do I start? Before I start. Okay, so everyone can see my screen and hear me well?
Yep.
Okay, thank you. So I'll be going through a little bit about the club status and our future events and everything. So first I will do a short introduction. I'm the president of the Supercomputing Club and I'm Jacob. You can either call me Jacob or Xiao Chen. And I'm currently a 3rd year computer science major at UC San Diego. Yeah, so let's start. So I know some of you have attended the club's GBM, so I'm gonna go through the slides in a faster pace, and there's also some changes. So how do I? Okay. So first, I'll talk a little bit about the club's overview. The club is currently in development, and we're planning for future events and communicating with other student clubs to see if there are potential like projects that we can hold together. We are also looking for new members. It doesn't matter if you're undergrad or graduate student, no matter what majors you are, we are pretty open to everyone. And also we're looking for officers who can help me and Mary and Joey to run the club. So yeah. First I'll talk a little bit about past events. We have attended Supercomputing Conference, as Mary said. And during SC19, there are 4 students selected to go to SC19 as a student volunteer. And I think 2 of us made it, and it was really fun because like we don't really have a lot of assigned tasks to do during the conference, so you are pretty free and you can attend those presentations. You can go to the communication events, and you will definitely learn a lot and make a lot of friends. So for SC20, which is last year, 6 of us attended supercomputing, the cluster competition. Since because of the pandemic, everything goes virtual, and we have to rely on the cloud platform called Azure. But prior to that, the competition usually takes place in person. So basically, you bring your hardware like CPU, GPUs, your monitors, and everything to the competition, and you set it up during the weekend before the competition, and then you run those application, which I'll be introduced a little bit later. And for SC21, which is this November, we're also looking for whoever wanted to join as a student volunteer, whoever want to attend the competition, yeah, and whoever want to be the mentor for the team. And yeah, and this HPC student program is the one that is taking place right now, and I assume that everybody knows it, so I'll just skip this page. And the Pi cluster project, we're about to develop the supercomputing system using Raspberry Pi, and we want to find a way that allows us to collaborate while maintaining social distance. So probably, like in my opinion, something like a distributed computing system or whatever. Yeah, we do have a previous project called Meteor, which uses, just give me a second. Let me open up this page and I'll go through it real quick. Not sure if you can see the page. Can you all see the website?
No, we do not.
Okay, let me share real quick. How about now? Can you all see this?
Yes.
Okay.
Yes.
So basically, it's 16 Raspberry Pi, and we connected up to 15 display screens, and this is, I think it's still at the center. So if everything goes on well and we can go back to campus, we probably can have a look at it. Yeah, it's I don't think it's very complicated, but it's a lot of fun, and you learn a lot of knowledge about hardwares and network and communications from the project. Okay. Give me a second. Let me go back to my slides. Okay. So about future events, I'm going to talk a little bit more in details about this supercomputing conference and the student cluster competition. As Mary said, we're ranked 4 out of 19. university, including MIT, ETH Zurich, and Georgia Tech, a lot of great university, and we're the second place in the US. So it's a pretty good result, and we're all happy about it. Yeah, so about the competition itself. So this year, the main challenge is going to be the 6 or 7 application that we have to run. And the first 3 of them are called the benchmark application. So for example, the high performance link pack, which is some benchmark to measure how fast your supercomputer is capable to calculate matrix operation, like matrix multiplication, and HPCG, something similar. In IO 500 is for the input output. So basically, you run those benchmarks, and whoever got the top score, whoever runs the fastest, got the most points. And the last 4 are the scientific application. The first one is called GrowMax, which is a platform or an environment that you can conduct experiments on like proteins and other chemical stuff. And the second one is CSEM. It's a software that can model the weather, and granted for not like if it takes long enough, it can predict the weather even after 100 years, 200 years of the Earth. So it's like the Earth in a whole. And the third one is called MEMXCT, which stands for Memory Centric X-ray Computed Tomography. And this is what we call the reproducibility challenge, which is so the MEMXCT is actually a paper, the best paper from SC19, the Supercomputing 19 conference. And our task is to reproduce the results presented in the paper and to compare if it's similar or it's different and the reason under it. So after you reproduce a result, you are also required to write a paper about your experiments and your learning process, which may lead to a further publication for the team. And the last one is called Minibyte, and it is a mystery app that nobody knows until the day the competition starts. It's a algorithm that compute random graph, something like that. And the competition itself is super hard, but it's super fun. Yeah. And next one is about our plan to SDSC 21. So if you are undergrad who are interested in attending this competition, you can either contact me or you can just probably just join the join the Discord channel. I have the link at the very end. So if you're not in the group, don't worry. I will share the link later. And if you are a graduate student, you can either attend as a student volunteer, or if you are pretty strong, experienced in HPC already or hardwares, you're also welcome to be the mentors of the team, and it will be super helpful. So no matter like you're undergrad or graduate student, don't worry, or even PhD student, don't worry. You're welcome on the team and to the club. In some plans, we'll hold talks with WIC, which stands for Women in Computing, which is a really strong, really large club on campus that worked for sorry, it's yeah, we're going to host a meeting with WIC, and the topic is going to be women in high performance computing, and it's going to be next week, and probably we'll send out a notification once the date is set. And also during week 5 and 6, we'll have a HPC 101, which is an introduction to supercomputing, with collaborating with Chinese Engineering Society. And during week 7, we'll have a mini student cluster competition at SDHack. So feel free to attend. And we'll also probably have quantum computing workshop either at later of this quarter or next quarter. So yeah, we do have a Discord channel, and I'll copy this link and wait a second to the chat. So if you're interested, you can just join this the Discord channel, and I'll be posting club events and workshops, agenda, stuff like that, and PowerPoints in Discord. Yeah, thank you. So any problems, and yeah, or if there's no problem, we can hand it back to Mary. Hey, Mary, are you there?
Yep. Yeah, I'm here. Sorry. Sorry about that. Okay, thanks, Jacob. I'll go ahead and share screen, get back to this. What I need to do is make sure I'm sharing this screen. All right, anybody have any questions? So what I want to do now is go ahead and go into just a basic overview of high performance computing. So I have to open up a different file though. So let me find this. Can you guys see this PowerPoint PDF?
Yes.
Okay, now I always forget how to put this into presentation mode. Does anybody remember how to do that? I always forget stuff like this. All right, let's just go ahead and work with this. All right, so get back to the beginning. Okay, so this is not going to be a very deep dive. It's just going to be kind of an overview and a drive through parallel architectures. And this is for very beginner people. So, hello? Oh, let me get my video. All right, so why do we want to have high performance computing? My serial code is working. Why should I parallelize it? Well, if any of you have done a lot of serious computation, especially people who are learning in the machine learning space, your laptop can do a lot of work, but after a while, it's just not enough memory. There's not enough storage. There's not enough compute power. I have two images here. One is my current machine, which has 8 physical cores on it that can hyperthread then to 16. And my previous machine was a MacBook Pro 15-inch with an Intel Core i7 that had 4 physical cores on it. And I was able to install parallel code, and I was able to make pretty good simulations of my ocean modeling project. But after a while, even simulating, I could not get scalability because of memory limitations. So I have a pretty good, some things haven't changed, 16 gigabytes of RAM, 16 gigabytes, processor speeds, even less on this one, but it's got a lot more cores. And I have a somewhat different graphics card. This one doesn't list it. But nonetheless, I can do work on my laptop, but after a while, it's just not going to be powerful. So then what do? You have to go to a bigger machine. That's why you're in this class. That's why we have supercomputing centers, and that's why we have cloud computing with resources out there that are actually high performance computers. You just have to build them. So everything has to scale up. And just a comment about machine learning. There's been some research into why are people moving from their laptops to the big machines is as the data gets so big, you can't fit it on your laptop. So you can't even move terabytes of data very easily. So you have to take the computing to the data. You have to be able to run these models that you don't know how long they're going to take to find a solution. You have until the learning is done. You don't know how many branches on the learning will occur. And so you need big systems that can help you run your code. We get quite a few people coming to our machines because they have to, not because they want to. So there are some gotchas about using parallel computers. Okay, so let's move on. My model that I did my PhD on was an ocean model. It was a 3D curvilinear model. So it had computations occurring in all dimensions. Most water-based fluid models, they tend to be 2D slabs with not a lot of vertical communication. So it was computationally intensive and data intensive and memory intensive. So it had to run on a supercomputer. And it took quite a while. So here's an example for what's called just a simple seamount, water flowing over a seamount. About 8,000 lines of code at a resolution of 1 kilometer per cell, which is smaller than the resolution of global models. But it would take for 6 hours of simulation, so water flowing for 6 hours along this seamount took about 70 hours on a computer. This is like 8 years ago or something. 200,000 iterations. So that's about 10 to the 14 operations. And then to run for a year, if I used a faster machine, which at that time was Jaguar at Oak Ridge, had 200,000 cores, 3 gigahertz, I could run that job in 0.3 times 10 to the minus 2 seconds. So it could go fast, but I have to get my code running on that big machine. So motivation for parallel computing is I can drastically reduce my run times, and now I can do the simulations that you need to run for environmental models is months, weeks, years, eons, or other big physics calculations. So that's the motivation, but to do it, it requires a bit of work. So we won't get to, the work of porting code, but it's always in the back of your mind. So I have 200,000 cores. Let's say I got on that big machine. I got an account. How do I do it? How do I use it? How do you coordinate 200,000 cores? So you need special libraries to do that. You need special hardware to move the data. And there's a lot of work that goes into designing big systems like Expanse. And if you want more information, go to the Expanse webpage. You'll get all that from us and take a look at the architecture. It's really interesting and really complicated and a lot of fun tasks and technical solutions. How do I distribute the data? Is my program memory or IO bound or both? How to distribute the computation around 200,000 cores? And then how do you synchronize results presented by 200,000 cores? So there's a whole world of libraries and applications. We'll get into those in the next few weeks. So what's parallel computing? Why do we need it? Large problems, of course. The science, hurricanes, forecast models for that. These hurricane predictions, and you watch them all the time when there's a big hurricane weather storm. They have hundreds of arrays. They use multiple models and multiple clusters, and they can take 12 hours to forecast out 3 to 4 days. And that's why when you look at hurricane forecasting, you might see it's right on for a day, and then the different models diverge, and you get this cone of results. And that's because it's all the probable errors that are being in each of the models, but they just try to get some aggregated view. And then you have applications that are very large data. Coastal ocean model that I worked on just for small was megabytes to gigabytes of output. So we need fast networks and we need to worry about power consumption. So there's different kinds of computing resources in the world of high performance computing. It's not just the CPU and the GPU, or there's also FPGAs and now quantum. There's the system that you put together. Your iPhone is a computer. My laptop is a parallel computer. It's got 8 cores. Then there's the larger HPC systems and clusters, and now cloud computing is being used by supercomputing HPC. So, and it spans everything from the compute architecture to archival and storage. Where do you put terabytes of data? Where do you put gigabytes of data? And then how do you move it around? How do you access it? That adds to the complexity of high performance computing. And the networks, you need if you have a lot of data, let's say you found a place to put it, how are you going to move it? SneakerNet? You know, you'd need like an airplane to hold enough SSD devices to hold the data. So we have to store it somewhere and then we have to move it. There's 400 gigabit per second networks that are now available. And Internet 2 is the entity that tends to support a lot of our nationwide networking. And then there's CENIC, which is the California Research and Education Network. They support a lot of different networks, including the Pacific Research Platform, which is a system around the Pacific area and the Asian countries and North America. So there's a lot of networks out there. They're always evolving. They're getting faster. There's parallel networks. And so 400 gigabit per second is kind of becoming more normalized. And then you have to visualize your data. How do you visualize a terabyte of results? Can you put every one of those elements on the screen? No, so you need a program that knows how to go through and pull out the key features of the data that you want to look at. And then underlying all of that is what we call cyber infrastructure. The networking, the archives, the storage systems, the HPC systems, the other components needed to do your computational work, they're all integrated with this middleware layer that's now global, more referred to as cyber infrastructure more and more. And all these components need to talk to each other. And we haven't even gotten to the user portal, the interfaces. What do you see when you're on your terminal typing and working on the computer? And you'll learn about that. So you want to have units of measure in your head. What's a megaflop? What's a giga? What's a tera? So I always try to include this so you can start thinking about exa. And then I need to put in a couple more because we're going beyond. We now have petabytes, or petaflop computers are more normalized, and now we're going to exascale computing. And that's requires a lot of work. There's a whole DOE initiative called the Exascale Computing Project. That's a 10-year goal that has been funded to bring exascale computing to more normal usage. And what do we need to do that? And they're starting to build computers. But one of the biggest problems is software management. So a couple of examples of big systems. This is the Oak Ridge National Lab called Summit. And it's 42 teraflops. And they don't list, sorry, I don't have the number of cores on that, but you can look it up. It's got hundreds of thousands of cores on it. And then there's cloud computing is also a resource that's becoming more and more used. We used cloud computing for the supercomputing student cluster competition, and they got some pretty good results using cloud computing, and you can do HPC on clouds. Cyber infrastructure, as I said before, it's been characterized as a research environment, but I would say it's probably moving more to commodity, but it's where the NSF is funding early development of advanced systems for cyber infrastructure, a large, broad number of resources, data storage, data management, information services. So where you see the S***, like service as a, or cyber infrastructure as a service, or computing as a service, or accounting as a service, that's all now depending more and more on this distributed cloud of services, this infrastructure for supporting cyber work. And so I had a project called Cyber Web, which had I like to show this because it shows these what we call the 3 layers of distributed computing. There's the user interface, and the middle one is where all the software lives, and at the back end is where most of the hardware lives, from the supercomputers to storage devices to other application services. Software as a service, that's the term, SaaS. But now it's SaaS because a lot of people are coining that term. But most of you will be at this end where you're coming in through an application, or you're on a laptop or your iPhone, or some other resource, and then you're going to use a lot of software. Even when you SSH onto a machine, you're using a middleware system that's pretty complex, and that SSH gets you onto one of these clusters, for example. So when you just go and do to Google and you do a Google search, you're using a 3-tier architecture where you logged on to Google, you contacted the Google server, it said, where is this question going to be answered? What's our database? And there's a lot of layers of systems behind that simple search. So how well are supercomputers working? So here is an evolution of computers at Oak Ridge. They're funded by the NSF, the DOE, the DoD, and they have some of the largest general computing, open as opposed to the ones by DoD that are restricted for defense related. So they have restricted access, but they've been making big systems since 2004. Summit is their newest system, 200 petaflops. They had Titan, which was 27, and they don't show the years. Maybe it's a linear graph, but you can see how things have been improving, but the time to getting faster is a little bit slower than the early years of what we called Moore's Law. That's because they're having to do a lot more work and be more creative to eke out more performance. And the excitement for quantum computing is that might just turn it all upside down. So that gets us to the top 500 is they track, and every year they do awards, and companies work hard to get some performance ranking in the top 500 supercomputers in the world. They've been tracking since 1994, back when I started working in the field. Megaflops, gigaflops, that was a really big deal. And now we're in the exaflop range, and petaflop are becoming more common. And this is 2022. So we're 2020, 2021, and there are some exaflop systems out there. And so you can see that this performance curve is starting to roll over, but it's not done. So there's still more growth that can be happening in the computational domain. So there's Moore's Law. That's basically Moore's Law processing power of a CPU per core doubles. I'll show you a curve. There's Gilder's Law for the bandwidth, Metcalfe's Law for how well that network is working, and Kreider's Law is density of information. So that's pretty important too, since we now know we're in the data decade or the data generation. Everything's about having more data than we can work with, which is what motivates machine learning. Is it allows you to plow through a bunch of data and synthesize out relationships in the data that you couldn't see very easily. And so that's why I think machine learning is going to be like the next calculator in 10 years. Technology growth laws, that just sort of summarizes these. I'm going to speed up a little bit. I want time to give you guys time to start getting started. So for networks, there's a top 500 for networks as well. So we can see there's increase in performance there. HPC systems, there's different kinds. So now let's drop back and look at the hardware. So you begin to understand the components. It's overwhelming at the beginning, and you're working with multiple layers of systems. So trying to develop a feel for that is part of what we're also trying to teach you. So there's parallel systems that are clusters or distributed, and the parallel system is Expanse, that big architecture I showed you. You log on, you're on a login node, you're going to run jobs, but they're not on the login node, they're on distributed nodes. We'll talk about all this next week, and I'll basically cover the Expanse 101 webinar that I did recently. You need really fast networks, you need to have some storage that's fast, and you need the software in order to be able to run things. And wrapping your head around all of these, you have to do it all at once. And then you have to start filling in the gaps. And there's a lot of head banging in the debugging process. So we'll teach you the very hello world level, that at least, if you can get hello world working, then you can isolate other problems with your more advanced code. So there's different kinds of memory. In this slide, there's two types that are mostly associated with CPU and GPU. shared memory and distributed memory. So this one shows A is a distributed memory. You have these different cores, or this is shared, sorry, and they all share the same memory. And that's sort of along the GPU architecture, and CPU also has shared memory. And then this one is a core, has its own memory, and then it shares memory with the other cores through a network. And now if you take those and you build one of each and make it as big as possible, at some point you need more than one node. A node now has multiple cores. And then you have to exchange data through the nodes. And then you have now some of the architectures have this is called non-uniform memory architecture. They have all of this on one chip. And then imagine you have 200,000 of these chips. So the software layer is pretty important. And sensing how you want to make it work for your application is important. And if you're a student, there's 1,000 billion jobs in this field that you could have so much fun with trying to solve all those problems. So parallel computing models. So there's concurrent, where a program is trying to do multiple tasks, like a stock market transaction, and those are often solved with parallel with p-threads right on your chip. The reason you can have your laptop running Zoom and you're answering email while I'm talking, while you're looking at maybe some program you're running, and you're looking at some Google search, is you have threads running on your laptop, and the threads are balanced to use up all the CPU resources that you might have. If you have multiple cores, there's a lot of swapping going in. The operating system knows how to do it. So we all actually live and work now in a parallel world. And then parallel computing is one where multiple tasks cooperate closely to solve a problem. And so talking about supercomputing, HPC, it's computational fluid dynamics, chemical computations, things that are tightly coupled. Then you could have distributed computing, where the program shares data with other resources to solve this problem. SETI at home is a classic example. Now there's many other problems out there, but I really am focused on high performance computing. Our latest system is Expanse, as I said before. It's got multiple components. Sorry about the scaling there. But we sort of talked about Expanse, but you can see now, knowing a little bit more about hardware, we have these different compute units that are designed so that the compute nodes and the GPU nodes are physically closer to each other. So you might eke out more performance if that's important to you, but nonetheless, you would have access to multiple of these nodes. One compute node unit has 728, there are 728 compute nodes, but one of these may, I forget how many are on it, it's got a certain number of compute nodes and a certain number of GPU nodes. And if you need more than that rack and that rack and that rack, for example, they have to exchange data. So there's a lot of work in network topology design. That's great fun. The specifications, here we go. 728 nodes, 128 cores per node, 52 GPUs, there are V100s. You can go find this on expanse.sdsc.edu. You can find all that information. We have a high-speed parallel file system called Lester and another high-speed system called Ceph, petabytes, 12 petabytes of storage there, and 7 petabytes on, and we're considered a modest system. So you can imagine what the larger systems have. And coordinating all of that takes quite a bit of work. Here is a larger, a deeper view into the scalable compute unit, which has got the CPU nodes and then the GPU nodes. So this one has 56 compute nodes. So 56 times 128. If your problem can't scale to that, then you're going to have multiple nodes. And then we have 2 aisles of these different SCCUs. Communicating with a high-speed network. And the way it's designed is it's easy to add and expand the system because you just order up another scalable compute unit, and they're actually in the process of doing that. Another system I show, although iGene BlueGene is still a fabulous system, it's kind of old in computing. But what I like to show is how it shows the physical size of how you start with the CPU chip with 2 processors back in 2002, and you put them on a board. And so this one has 8 chips per board. And then you put the boards into nodes that live on a rack. 128 boards, they fit onto this rack. And so you see it's already getting bigger. And then they had 64 cabinets or racks for iGene, the Blue Gene system, and how much space that takes in a room. Now, each year we get smarter, we condense more um, processors onto a chip, et cetera, but it's still got the same growth. That's why when you look at the picture of Expanse, it's big. It's 13 racks. So that's the kind of scaling of the physical hardware. And more systems. We want to talk about briefly architecture. So there's CPU architecture, GPU architecture, FPGAs, and now quantum computing. How is it built? How does it work? So this is just some of the features of the looks like I have a type of an Intel Xeon processor, which has the dual Intel Xeon dual processor hyperthreading. Hyperthreading is good if I have 8 cores like I have on my laptop and I turn on hyperthreading, I can get as many threads as I want. That doesn't mean I'm going to scale. If I try to do, I had one student who we did a scaling study and he got 500 threads to scale on one node on this machine that only had 18 cores. I said, how'd you do that? And he didn't realize he was spawning all these P threads and the performance was bad, but he called it scaling because he could get them to run. So hyperthreading is a two-edged sword. You have to make sure that the threads are properly allocated. And that's a problem with OpenMP and other technologies like that. You have to watch how your threads are managed. But nonetheless, hyperthreading does allow you to get more work done and you duplicate the architectural state. What this does though is does give you an idea of, where's your CPU, what kind of cache do you have, and cache on the CPU chip and even on the GPU. You have to worry about where am I using the memory. And then you have different operations that have to occur as you move your data around. So this is a CPU with a few cores, and then there's also the GPU that has thousands of cores. So GPU is very popular because what they do is they have thousands and millions of cores that are pretty much atomic units. They do very small amount of work, but a lot of them do it together. And so you have to, couple of complexities. GPUs right now, they have to be controlled and connected to a CPU. You can have multiple GPUs connected to that CPU. Between the different devices, you have to exchange data, for example, and that would be done at the CPU level. Then you have to get the data down to the GPU. So there's some latencies there. But once you get your data on the GPU, you get good acceleration, often without changing your code. And that's why it's very popular. So there's some gotchas that they're learning to solve, but it's these smaller, think more efficient, like instead of a CPU that does a lot of calculations, the GPU might just do 1 + 1, A + B, or a little bit more complicated, but it would do a whole lot of those at one time. And so you would just pass different workloads to the GPU. There's a lot of different models, but we have both of those on Expanse. When you think of CPU, even GPU, this is more a CPU, there's a memory hierarchy. And this is important to realize because you may not ever get to the point where you have to worry about what level of cache am I using, where is my data stored on the CPU, but you should be aware that they are there. So you have your CPU with the registers that the central processing unit will use and some data in there. And then the L1, L2, and 1.3, those are organized by how far away physically are they from the CPU, and also how much data is in them, and what is the communication time between, how long does it take to move data from the L3 cache down onto the CPU? Well, first you have to get that cache onto the L2, which is a little faster, and the L1, which is a lot closer. And so what you do is you take a chunk of L3, you move it to L2, you take a chunk of L2, you move it to L1. The CPU is always moving data around for you. And then you have to get your data to the main memory, and then you want to get it accessed out on the storage. And so there's different metrics of scaling times, nanosecond from L1, tens of nanoseconds, hundreds of nanoseconds. And you think, well, that's not so bad, tens of nanoseconds. But when you're talking about a terascale data set, that's a lot of time. So you have to get your data on there and get the work done. So remember, sometimes you might get surprisingly poor scaling if you haven't thought about where's my data and how am I getting it to the CPU or the GPU. It's the same concept, another factor. And then there's the network. And this, I like this because it shows a layout, a nice clean layout of a interconnection network for the Lone Star computer at TAC. And so this is 512 compute nodes on these different 32 racks. And you want, what you try to do when network designers design the network, they want to guarantee for you that if you're at, let's say this is core node 0 down here in the lower left and node 513 in the upper right, counting from 0 to 513 to 511, you want the communication time between these two to be about the same as if you were doing node 1 to node 0, because in general, you don't know which exact physical node you're going to get. You could require it, but you want some guarantee that the time for signals to travel between the different pieces of hardware on the system are as uniform as realistically possible. So you might accept the fact that if I'm all on one rack, it's going to be faster than if I'm end racks, but you don't want it to be significantly longer, because can you imagine the complexity of communication on Summit, where they have 100,000, hundreds of thousands of cores. So they want that communication to be well balanced, and that's part of the exascale computing project, is to work on, they're doing a lot of the management now by software as well. So this is just a simple idea, this is from 2007, but interconnection network concepts are always about the same. And they have different topologies. This is a 3-dimensional torus, there's a tree, and then this is the tree-based topology of the network, the Ethernet, the network that you go out and try and get information from. So how things are interconnected is as important. Have you ever thought about what kind of web serving systems, internet service providers, does my request to Google some piece of information go? Hundreds of thousands of routers, possibly, certainly hundreds of them. And it turns out Google will take common queries and fetch them and stage them in distribution network nodes, so that if people ask for something common like Joe Biden inauguration, right, then that data is closer, and they're going to use a probability algorithm to determine, well, what should be at these different nodes. But when you go out and if you look at the topology of the network that you use every day, it's pretty complicated. It's another great field of science if you like that. And then of course we can't start our class out without acknowledging quantum computing. And as a physicist, it excites me a lot to see this work making progress. I know there's classes now being taught at UCSD, and the idea is they have this unit of measure for performance called the qubit. It's not exactly the same as a floating point operation, but at some end of the day, they're working on the metrics for what kind of qubits do we need to do machine learning, and when will we get there? And I apologize for the lack of scale, but you can see that actually quantum computing qubit, it's been around for a while, but now all of a sudden we're in a domain where we can actually start looking at it seriously, because there's value in developing full systems. So the machine learning curve is right here. It needs 1,000 qubits, and I think we're not quite there yet. So when you start getting some kind of return on the investment of time, both in building quantum computers and your time in learning how to do quantum computing, we're a ways off from that, but we're not far, and it's going to change things. Right now, this is, I think it's an IBM. I'm not sure. That's what they look like. And part of it is you're looking at the hardware needed to take an incoming signal and reduce it down to where all of the energy can focus on some little tiny pinpoint down inside, kind of like focusing a laser beam, but multiple laser beams. And a lot of the hardware you see here is frankly dedicated to noise reduction, because as they go through each of the stages of the quantum computer to get everything down to where they're down at that qubit level, remember quantum computing is making two waves interact, then they have to get rid of the noise. So they're trying to solve a lot of problems there. It's going to be an exciting field. So acknowledging quantum computing, and maybe in 5 years we'll have the SDSC quantum computer. That would be fun. Ethernet, of course, is getting faster and faster. And this one is still it's a pretty old one. It's thinking that gigabit is pretty exciting, but we know hundreds of gigabits are now the norm. Infiniband this was just coming in the early 2000s, and now it's sort of ubiquitous. But they they changed the communication protocol. So it made things a lot more optimal. And now we're seeing it becoming ubiquitous. Infiniband networking on an HPC system is now the de facto. It's not the same as TCP/IP, so it's a little bit different. All right, parallel algorithms. So here I'm going to give you a very simple example of how to parallelize code, and then I'll be done. Just a few more slides here. So we want to add some numbers and put them and get an answer. So typically you would go through a certain number of numbers, and we're going to run a routine to compute the next value, some algorithm, and then we're going to add the answers. And in serial, this is pretty simple. I can do it on my laptop pretty quickly, but if n is, petascale, or the compute next value is complicated, this could take a long time. So we want to parallelize that. So I have p cores where p is a lot smaller than n. It doesn't make sense to do parallel computing if it takes longer to fire up your 10,000 cores than it does to calculate n. So there has to be some payoff for parallelization. And so each core will do some portion of the work. It has its own variables, and the variables do some work, and then you want to sum the results on the core, and then somehow we have to get some controller to get all the data and assemble the data. And there's many models for doing that. So after each core, here's sort of the process computes its work. It's a private variable in MySum. And then if we have 8 cores, we have to the controller core would then call these cores to get the numbers and sum them all up. So when they're done, though, we want to form this global sum, and the master core, it does the work. And so how do we arrange that? So the master core, I'm the master core. If I am, I'm going to sum my number, and then for all the other cores other than me, I'm going to get a value. I'm going to call them up and say, hey, core number 2, do you have your value? And maybe it's done, maybe it's not. So in this model here, I'm going to wait. So are you done with your work yet? Are you done? Okay, you're done. Great. I've got a number, and I'm going to add it to my sum. And for each core, and I'm right now in this simple model, I'm going to start with the first core, core 1. I'm core 0. And then I wait for core 1 to finish its work. And then I go and I ask core 2 to finish its work. And to first order, this could give you some performance improvement. But what if core number 7 dropped out? What if it got lost? What if it's like really slow because core number 7 randomly ended up with a whole lot more work than the other cores? Well, I have to wait. So this one is going to work and collect data from the cores, but it might not be optimal. And we'll look at other solutions for that. So here's my sum. I keep each of the cores have their sum. The global sum should be 95, and the master gets all the values from the other cores and sums them up. So you want to make sure that you could maybe get some optimization and reduce the master core workload. And I apologize. I think these days we're using terms other than master. So controller core, I should update my slides. And I apologize if that is offensive to anybody. I will fix my slides. So we want to pair the cores so that you can get some speed up by letting groups of cores communicate sort of in a tree-like gather process. So we're going to try that. And now we only have to make 4 calls instead of 8, and it reduces the time. So this is what we call a tree structure addition. These cores work in parallel. They each, the even cores will collect data from the odd cores, or vice versa, and then they gather their data. And so instead of making 7 calls, only 3 calls are required. And you can say, oh, that might make things run a lot faster. So you get parallelization, gives you speed up because you divide the workload. And then you also get speed up because algorithms exist on the machine that do things more quickly than a simple linear call, connecting to each node and trying to get the answer from them. And there's a lot of work. That's why when we work in parallel computing, we use parallel libraries. And we'll talk about some of those over the next few lectures and what that means. But just if you can get this concept that by doing things in groups collectively, that we can reduce the time to solution because we reduce the communication required between the different neighbors. Imagine you're all sitting in a classroom, and this is what I would do if we were in person, and we have all of you sitting in a desk. Each of you are in a row and a column, and you have a space where you live. And what I might say is, everybody, I give you each a bag of money, and I trust that you're going to add the money up in your bag and pass the money value forward, but you can keep the bag. It's not that much money. And so I say, everybody pass your sums to the person in the front row, and then all the front rows will turn in results. So this is the mental image you can have in your mind about how parallel computing can improve your computation time. So we could do what I just described as task parallelism or data parallelism. In task parallelism, I just gave you each a bag of money. I didn't check to see that you each had 10 bills. Besides, one of you might have more $100 bills than $1 bills, and it would you would get your answer faster. So it just, the task is the work that we're passing out, but the tasks may not all finish in the same time. So you need software that synchronizes that work. And then data parallelism, again, you might distribute the data evenly, or you might have something that's a hybrid of the two. So we want parallel hardware that can manage that all quickly. So we're moving to HPC hardware, and the NSF EXCEED project, Extreme Science and Engineering Data. I always forget what EXCEED stands for, but it's a group of resources funded by the NSF. They're all high performance computing resources, everything from compute to storage, and you're going to have access to that through this class. And so you'll log on to the portal, and we'll start guiding you through making accounts. So www.exceed, I think you want to go to, I'll put it in here, portal.exceed.org. All right, and so I think that wraps up my talk. That's my last one. Next class is next week, where we'll be going over some of the basics of using the cluster. I mean, we'll help you get on there and do some activities, although there's some of that is your homework for the week, your assignment. And then everything's posted, and then you can't get these done until you have your account. The account can take days to get. And so if you put this off until next Thursday, you're going to end up a week behind. So please, 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 we're going to hang around. The students from the club are here to help. If you have any problems, we'll help you all get your account set up and ready. And then it'll take a day or two for SDSC to get notified that you applied for an account. And as part of that process, as part of that process, let me get back to my talk. As part of that process, we'll help you get your Expanse account. And then I have a form that I have you sign on. And in it, your portal ID, I get your portal ID. I can't add you to my allocation if I don't know your portal ID. I won't get your portal ID until you fill out this form. And once I get that, then I add you to my allocation. Once I can do that, then Nicole Walter, who will step in and create your account. And then that takes about 24 hours. So I can get, as soon as you give me, over the weekend, I'll even be looking. I want to get you guys on so you can try to log on. If you've never logged on, we need to know that so we can figure out how to help you figure that out. We have some basic tutorials for that, which if we all go to the GitHub repository, this is our open HPC training repository. There's many different repositories in there, and they're for you to look at. If you're interested in notebooks, and we'll talk a bit about that next week or the week after. This is Expanse 101. You can get a hold of our documents by going to the HPC trainings page, which has got documents on Expanse and how to run notebooks in our environment. These are tutorials that are focused on making sure you can do the work you need to do on our machines. They're very basic. These are entry, which is why they're called 101. So take a look at those. If we're in the tutorial, where is it? HPC training. In the past, I've had these in a different repository. Each week, and they'll get added in. It tends to be a bit dynamic, but each week we'll have a folder with some instructions and links to the material. These links will be uploaded today, probably while you guys are getting your account set up. So you've already registered. If you haven't registered, I think Cindy's been in touch with you. It's not too late. We're open for another week. People who start next week can get caught up pretty easily. What we covered today is also covered in these tutorials. And so I'll get mine uploaded. And so you need to register and then get that portal account, get that portal ID, go to the enrollment form. It's pretty straightforward. Just a few things about you so we can figure out who we've got. And then I'll get that information, and then I add you to my portal allocation. And at that point, you'll get that account created. And then once you get your account, you'll be able to log on. Well, this didn't turn out right. I'll clean that up. There are a few skills that we recommend you have, and this is in one of our training repositories, the basic skills, basic Linux. If you don't know basic Linux, you might struggle in this class, even at the level we're doing it. But if you ever think you're going to work on HPC systems, you might as well start learning them now. And this is from just how to move through a directory. It's not DOS. It's not at all like a DOS, but there are some similar commands. And then how to connect and how to run a notebook, what's interactive computing. And even I acknowledge that some of you may have never used GitHub. So we have a basic GitHub, because you do have to be able to know how to clone these repositories. They're all open source, so you can clone them and download them. You just can't upload because you're not on the team. So your homework for the week is to try and visit some of the basic skills and try to run these commands. For example, Linux, these README files are written so that you can log onto the computer and run that command. All of the markdown files, we try to make it so if it is a tutorial where it's teaching you how to do things on the supercomputer, that we have it set up so you can run those exact commands, cut and paste. So date's pretty straightforward, but for more complicated ones, then we have some more information. with that, I'll turn it over to you guys to start getting your account. So again, you want to go to portal.exceed.org and you would create an account. So I'm going to pause right here. Are there any questions from anybody? I'm going to stop sharing for a moment so we can see people. Anybody have any questions they want to ask? The organization would be the San Diego Supercomputer Center. Good question. If you already have an Exceed account, that's fine. Just get started on the basic skills. If you don't need the basic skills, just take a look at it. And then what we want to do is you could go into and create the homework folders. That'll tell me that you've already got your basic skills. So just take a look at them. Nice to see a few familiar names and faces. That's great. All right, I'll go back to screen sharing. So we have create account. The organization, right. You will be able to access the recording right now. Joey, you can stop. No, let's keep it recording for a little bit. You can access the recording. We'll put the recording up on a place where we have some interactive videos. I want to collect them as part of the HPC user training. There'll be, we'll post a link on here on this page. So we'll have a link to the recordings and a list of them on this page. Does that sound like that can work for you, Cindy? We have, I think she's muted, but we have a person who takes a webinar. It's very cool. They take a webinar and they convert it to, they get the soundtrack from it, the text, the audio, and they clean up the audio. And the webinar is a recording of the slides that I went through. And then he puts in timestamps for wherever in the talk a slide appears. And then you can search the content in form of the audio text, or you can slide through the recording, find the slide you're interested in, and then go look at the content that was presented with it. If you want examples of what other interactive videos look like, if I go to this page, this page, and you can see a bunch of our different events, our past events. For example, the Expanse 101 has a link here, which is the interactive video. So you don't need to hear anymore. Okay, so you can hear that. But if I click on running jobs, the video advances to that point and I get the transcript that's associated with it. I can go into the transcript and that will take me to different parts. So we're working, this is a brand new system that we're working out for our presentations, but we'll do the same thing hopefully with these. Initially, we'll just have the webinars up, but we'll get a link for that from the homepage for the user training series.
Mary, can you hear me?
I can hear you.
Oh,
yes.
okay. It was part of my microphone. I kept talking. I was like, wait, what's going on? Okay, so quick question before you go into the Q&A, the chats. I think there's a few questions regarding the portal ID. Is there any restrictions for, we do have some non-US registrants. Is there any restrictions for that, for those to get accounts?
No.
Okay.
Nope. As far as I know, there's not, and Exceed will make a determination. Most of our systems are not classified.
Okay.
There's no requirement.
Okay.
And so in here, I think you can find, if you can't find, maybe it's the University of California. The Supercomputing Center might show up in here. I think if you type So we don't want that. Did that show up? No, it didn't. So we might want to go ahead and use University of California. Did that show up? I'm sure it's here. There's a lot of University of Californias. There we are. And then down here, you could put in San Diego Supercomputing Center. Oh no, this is maybe about you. It looks like it's about you. So, and again, if you're having trouble with the portal, let us know. Nice. You can choose UCSD as your organization. You can choose either one. You may have a different organization that appears here. It doesn't have to be SDSC, and it does not have to be UCSD. So they have quite a few. I don't see that they have other, which is interesting. Although these are free to qualified users, that doesn't mean everybody is qualified. These are for research supported by the National Science Foundation or training. And even if you're from a private company and you're a local, we'll check that out and make sure it's okay. But in general, I think it's fine. I don't know if Mahi is still with us, but any has any thoughts about that.
Mary, did you see Mahidar's email regarding the accounts? Just wanted to make sure that you.
No, I didn't. I haven't seen my email.
Yeah, so
Joey,
you
you
don't mind
could
looking at that actually.
Okay,
So
I will.
it's
Okay,
regarding-
Joey, you can stop recording. Thank you.